Here are the notes for day 100. I couldn't find fireworks or anything like that, so you'll have to settle for a Mardi Gras mask. Yay, day 100. So anyways, the topic is alternating series, and what's happening here is that we finally have a bunch of series that will go back and forth, as the name implies, alternating signs between positive and negative. If the exponent is n or n plus 1, you're either going to start with negative, positive, or it's going to go positive, negative. In either case, the signs are going to alternate, and they must alternate every turn. The alternating series test will help us decide whether an alternating series converges or diverges using these two steps. Take the limit of just the sequence, ignore the alternating part, just the sequence, and if that equals 0, which comes from the nth term test, then we take the additional step of checking to see whether or not the terms of the sequence always decrease. The nth term test, when the limit equals 0, is inconclusive, but for alternating series, if we can prove that they also decrease, then we have a convergent alternating series. So 2 examples of that. First step, take the sequence part, ignore the alternating part, take the sequence part, find the limit as n approaches infinity, use LHOP if you have to, but we pretty much know that this reduces to 1/4, which is doesn't reduce to 1/4, it reduces to 2/8n. As n approaches infinity, we get 0. So first step passes. Second step in the alternating series test is to see if the terms decrease. For this one, I decided to turn it into a function and find the first derivative. There's a couple different ways of doing this, but in this case, derivative isn't so bad. Use the quotient rule, ho d high minus high d ho over ho squared. The denominator is always positive because it's squared. The numerator, after you distribute and combine like terms, you wind up with negative 8x squared minus 6, which will always be negative, no matter what you plug in for x. And in this case, remember, we're starting our index at 1, so x represents the n index. First term and second terms are both negative, so the overall fraction is negative. So both steps in the alternating series test have been satisfied, and we have a decreasing sequence of terms, which means we know that this alternating series converges. Second example is much faster. When we go to try the nth term test, we wind up with a limit that's 1/2. That does not equal 0. We know that that sequence diverges, so the series also diverges. So before we go more in depth in the alternating series test and some different types of convergence, alternating series have a unique property in that you can estimate the error, or how much your nth partial sum differs from the overall total sum. You can estimate the error by looking at the next term. So what that means is, down here, if we want to figure out how many terms are needed to approximate this sum with less than 0.005, error less than 0.005, we're going to just plug in numbers for n and list the outcomes until we get a value that's less than 0.005. Now, error is an absolute value, so all I need to look for is 0.005. It doesn't matter whether it's positive or negative. So plugging in 1 to this, we get 1/4. Plugging in 2, we get 1/32 negative. Plugging in 3, we get 0.0052, awfully close, which means finally when I plug in 4, I get this value, which is below 0.005. So since this term is less than the error that I was looking for, this is my error term, and I know that summing the first 3 terms will produce an error less than 0.005. The error is actually 0.009765. So, well, less than or equal to that value there. So I'm going to find S3, the sum of the first 3 terms, the partial sum, and now I can provide an estimate for the sum by saying if the error is going to be less than the next term, the error from the first 3 terms is going to be less than the 4th term, I can take this absolute value and expand it, S minus S3. Well, I just calculated S3 over here, and I put both positive and negative as bounds on the inequality, solve for S, and I can see that the infinite sum is somewhere between 0.222973 and 0.224927, which you can see is less than 0.005. The difference between those two is less than 0.005. So that's pretty powerful. This formula only works, however, for alternating series. This is the first case where we've been able to approximate the infinite sum using a partial sum and know what the error is going to be. Okay, so back to alternating series. Alternating series have a very strange kind of conclusion that produces 2 types of convergence. We have what's called absolutely convergent or conditionally convergent. And while this statement, which comes out of the book, is a little bit confusing, there'll be a pretty good summary on the next slide. But the steps that you're going to go through are listed right here. So we want to know what kind of convergence, if any, this series has. So I'm going to start with the nth term test. I get the limit of 1 over n is 0. The nth term test is inconclusive, so now I'm going to go to the alternating series test. Well, the first step in the alternating series test is the nth term test, so I get 0 there, which is good. So don't confuse those two steps. The nth term test is inconclusive, but since it's an alternating series, I actually want that because that's the first step of the alternating series test. And now all I need to do is prove that the terms are decreasing. So I say, is the nth term going to be greater than the next term? Well, if I do some cross multiplying, and I know both of these are positive, so I can cross multiply with an inequality because n is an index that starts at 1 and only goes up. I have the statement 1 greater than 0, which is true for all n. Both parts of the alternating series test passed, so I have convergence. Now to see what kind of convergence we have, I go back up to, not the alternating series, but I look at just the sequence part, 1 over n. Well, we know that that's a harmonic divergence series. So since the alternating converges, but the sequence, the series from just the sequence, not the alternating part, but the series itself diverges, then we have what's called conditionally convergent. And again, you'll see a summary of this on the next slide. Next one, same idea. Here I have an alternating series. I'm going to perform the nth term test. Take the limit of just the sequence part, the a sub n. I wind up with plus or minus a quarter. That doesn't equal 0, so this diverges. The alternating series diverges. So a summary and a little bit of a roadmap on how to do these things. The alternating series test says if both of these steps are satisfied, the limit of the sequence of terms is 0, and you can show that the terms are decreasing, then you have a convergent alternating series. Here's a summary for the overall process. Start with the nth term test. If the nth term test on the alternating series diverges, in other words, if the limit of the sequence of term is infinity or does not equal 0, then you have divergence and you can stop. If the nth term test is inconclusive, you take just the positive part, ignore the alternating part, and check to see if it converges. If that converges, you have an alternating series that absolutely converges. If just the positive part, the sequence of terms without the alternating part, diverges, then you perform the alternating series test. And if the alternating series test converges, you have conditional convergence. And if the alternating series test diverges, then you have divergence again. So why do we need this absolute convergence and conditional convergence? Well, it gets a little bit complicated and a little bit scary actually, but what happens is if you have something that absolutely converges, then the rearrangement of the terms does not affect the sums. But if you have something that conditionally converges, what that means is that you could take those numbers, the positives and negatives, add them up one way, rearrange those numbers, add them up, and you'd get a different sum. And it's very strange, but there's a pretty good example of that in the book that we'll be walking through. You don't really need to worry about finding this actual sum when you're all done. You just need to be able to label the alternating series as either conditional convergence or absolute convergence if it converges. If it diverges, there's just one name, divergence. Okay, that's it. Congratulations. You've done 100 days of calculus.